All right, our final speaker for this session will be Bob MacDowall, who will be talking about the lunar payload for radio wave observations at the lunar surface of the photoelectron sheath, or ROLSES.
Okay, you people need to get out of here in 15 minutes, so let's go. This presentation is about a NASA-provided lunar payload that we're developing to make measurements of the photoelectron sheath at the lunar surface, which has the acronym ROLSES, and it sort of follows other activities that, this doesn't work. This, the co-Is and collaborators listed there include Jack Burns, and Jack's NASA Lunar Science Institute and survey teams have worked on lunar radio observatories for a long time, but years ago they didn't get funded. However, now things have changed, so hopefully there will be some interesting things. And ROLSES, of course, is a 10-day mission, so there's only a finite amount of result, but let's look and see what it will be. No? Yes. Okay, so we'll have an introduction and look at the science and technical objectives and the hardware review, and then you'll go out the door. As a status, the proposal referred to the stereo spacecraft WAVES instrument, but we're building the digital electronics using the design of the Global Ecosystem Dynamics Investigation Board, which is an experiment on the International Space Station. Frequency range of 10 kilohertz to 30 megahertz. But these high frequencies are intended to provide support for other lunar radio mission proposals. There are four monopoles on this lander. In the figure, you see these brown stacer antennas, and the commercial lander that is supposed to take ROLSES to the lunar surface is the Nova C provided by Intuitive Machines, and the landing site would be their landing site is in Oceanus Procellarum. Don't do that. Now what? That works that way. Now that wants to work, but that's not what I want you to do. Why are we going the wrong way?
It should be the big button is to go forward.
Oh, that's the button.
Yeah.
Is that right?
Yeah.
Thank you. Okay. Multiple funny things. Anyway, so the rectangle there shows Oceanus Procellarum. And moving on, the lunar surface photoelectron sheath has been modeled by using various simulations. In the one shown here, from a model from Pape and Oriani. You see the results for plasma at different times, and solar wind after a shock has gone by, after a solar flare, in the environment of a CME, and you see that it does have a substantial change for the density, order of magnitude. In 10 days, we don't know how much of that we'll see, but we hope to see something. In any case, at 1 meter, the density is about 10 to the 7th electrons per meter cubed, which is a frequency of about 64 kilohertz. Here's a different model from code from Mike Zimmerman, and if you had memorized the plot from the previous page, you'll see that this one is somewhat different, but the results are not dramatically different in the sense that here, at 1 meter height, it's the density is 3 times 10 to the 7th per meter cubed. So ROLSES wants to measure these values, and just based on the thermal noise spectrum, possibly on wave activity at the electron plasma frequency, and by absorption of the radio spectra of remote radio sources at frequencies at and below the electron plasma frequency. So other things that we will see from the lunar surface are radio sources elsewhere. In this plot, which is 24 hours of data covering 0.01 to 10 megahertz from the Wind spacecraft WAVES instrument. It shows, to first approximation, what ROLSES will see from the lunar surface. There is, one thing we will see is the radio emission from the Earth's magnetosphere, auroral kilometric radiation. We'll see solar radio bursts. We might see Jupiter, and Wind at this point, as it has been for the last 20 years, is out at the L1, the solar Earth L1 Lagrangian point. So the RFI from Earth that it sees is quite weak, but it still sees the sun. Another phenomenon that we might detect is in radio astronomy instruments on spacecraft typically detect dust when the particles strike the antennas or strike the spacecraft, because the impact releases electrons and ions from the surface, which affects the photoelectron environment and creates electrical signals that are readily detectable. And in this plot from Cassini, you see what the radio instrument sees when it flies through through Saturn's F-ring. So ROLSES might detect dust impacts on the lander or on the antennas if it's a cloud. Our time resolution is not designed to detect individual dust particles, but it could detect clouds of dust. So one more thing that we are considering that we might see is the radio waves coming down from whatever sources are out there, especially the more intense sources, will likely penetrate the lunar surface, and they might be reflected back up so that you detect them. And this tells you something about the surface below the lander. A better example is the Apollo 17 Lunar Surface Electrical Properties SEP instrument that made such instruments at 6 frequencies. There was a signal generator that created the radio waves, and then the detector was on the rover, so that they made measurements at various distances from the signal generator. And the Icarus article by Grimm describes the recent analysis of these results, and because no deep interfaces were detected, the thickness of the torus littrow volcanic fill where the rover was moving around must exceed at least 1.6 kilometers and possibly twice that. So reflections can give you useful data. One technical result that we want to obtain is what is the current level of terrestrial radio frequency interference. In this shown in this plot, you see a 24-hour plot from the wind waves instrument, and again the frequencies from less than 1 over 10 megahertz. And so all except for a few weak solar radio bursts here, this is during solar minimum in 1999 on April the 2nd, when the WindWave spacecraft flew very near the moon. You see all of these transmissions coming up from the Earth, and it's a considerable amount of RFI, which would be a major noise source for a near-side lunar surface-based radio observatory, although we believe that we could still image solar radio bursts because they are very intense, and you'd have to just remove the noise from the source. So anyway, we would like to know how much that noise spectrum of terrestrial radio frequency interference has changed since 1999. So very quickly, this is the diagram. So we have antennas and preamps, and then antenna deployment electronics, and data processing electronics, and power regulation electronics, and possibly a cooling system, because on these landers the electronics get to see the lunar surface, so they may get quite warm. Our thermal engineer is working on this at the present time. Okay, some of you will want to know these things, but let me just point out again that the frequency coverage is 10 kilohertz to 30 megahertz, and we'll be getting data at about 17 kilobits per second, so it will be a good set of data. This is the electronics board from the Global Environment Dynamics Investigation. It's actually a LiDAR experiment on the International Space Station. So the daughter board at the front of the electronics will have to change because our frequencies are a lot lower than LiDAR. But our engineers at Goddard want to use the same system. The data acquisition will take place in 2 bands, 10 kilohertz to 1 megahertz and 300 kilohertz to 30 megahertz, with the overlap helping to confirm calibration. And it will be analyzed using a spectrometer device that the engineering people at Goddard like. The frequency band resolutions are indicated. As I said before, this time resolution will probably be 5 seconds, although since Intuitive Machines has more communication volume available, we might be able to do a higher time resolution. So the schedule is, we need to deliver, well, we plan to deliver in July of next year, or at least by August of next year. And then Intuitive Machines would launch on in principle at 7/16 in 2021 and land on the moon on July 22. So in summary, the ROLSES NASA-provided lunar payload will focus on determining the density and scale height of the photoelectron sheath, as well as detection of solar and terrestrial radio bursts, to demonstrate that could be done from the lunar surface, and the possible detection of clouds of dust impacting the system, and the current level of terrestrial RFI from ground-based radio transmitters, and maybe we might see reflection of incoming radio waves from the lunar surface or below the lunar surface. So anyway, we're looking forward to delivering ROLS next year and obtaining data from the lunar surface in 2021. Thank you.
Any questions? I guess I'm curious why the 10-day mission lifetime was chosen. I mean, was that all you need, or is there some sort of limiting factor for that?
Well, this is a factor for all of the commercial landers at this point. They are, although they're pondering the possibility, they are not designed to survive lunar night. So they will try to land you as close as possible to dawn, and so you'll survive, the lander and the instruments will survive past dusk. So it could be a little more than 10 days, depending on where they land and so forth. But and also how quickly the thermal environment succeeds in destroying everything. But without a design to survive lunar night, it's a approximately 10-day mission. Yeah. So. That's actually there have been, of course, conferences on the subject of surviving lunar night, and it is an important activity to be worked. I mean, there are simple ways to do it, but it requires too much battery mass or radioisotope thermal generators, so that it's not simple. It is. The nature of the moon, with its very slow rotation, complicates long-term survival.
So I was just wondering if the local topography of your landing site could have a measurable effect on the measurements you're making.
Yes, I think in general that is true. What? We can go forward with Oceanus Procellarum, but different at different locations on the surface the photoelectron sheath density and scale height will actually be different. So you're not providing universal measurements. Any comments, Bill?
Sounds good to me, Bob.
Okay.
Okay, I think we're out of time, so